Alright guys, how many times have you been hanging out just minding your own business when BAM! Electronics. They're everywhere, right? And they all rely on electrical circuits. But the cool thing is, you don't have to be some kind of electrical genius to understand the basics. So in this series, we're gonna break down the fundamentals of electrical circuits into bite-sized pieces, even if you don't know the difference between a capacitor and a flux capacitor, which by the way is a totally real thing. In this first video we're tackling DC circuits. We'll be your guide through the wild world of resistors, voltage, and current. All the good stuff you need to know to get started. Don't worry, we'll take it slow and steady, like a sloth in a race. But a sloth that actually understands electricity. By the end of this video, you'll be able to impress your friends with your newfound electrical knowledge. You'll be like the go-to person when someone can't figure out why their Christmas lights aren't working. Which, let's be honest, is a superpower everyone needs during the holidays. First things first, let's talk about what an electrical circuit actually is. Imagine a closed loop, kind of like a racetrack, where tiny little charged particles called electrons can zoom around. This flow of electrons is what we call current. Think of it like a river, but instead of water, it's electrons flowing through the wires. Now for those electrons to get moving, they need something to push them along. That push is what we call voltage. You can think of voltage like the height of a waterfall. The higher the waterfall, the more potential energy the water has to flow downstream. Similarly, the higher the voltage, the more oomph those electrons have to move through the circuit. And what slows down those speedy electrons? That's where resistance comes in. Resistance is like the rocks and obstacles in our river analogy. It makes it harder for the electrons to flow freely. We measure current in units called amperes, or amps for short. Voltage is measured in volts, and resistance is measured in ohms. And get this, these three fundamental concepts are related by a super important law called Ohm's law. It's like the holy grail of basic circuit analysis. But we'll get to that in a bit. For now, just remember, current is the flow, voltage is the push, and resistance is the drag. Easy peasy, right? Alright, let's talk about the law of the land in the world of circuits. Ohm's law. It's like the traffic light that keeps everything running smoothly. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across it, and inversely proportional to the resistance. In simpler terms, if you increase the voltage, you increase the current. But if you increase the resistance, you decrease the current. Think of it like a water hose. The wider the hose, less resistance, the more water can flow through, more current. But if you crimp the hose, more resistance, less water will flow, less current. And just like we have traffic laws to prevent chaos on the road, we have two more fundamental laws for circuits: Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL. KCL states that the total current entering a junction in a circuit must equal the total current leaving that junction. Basically, electricity can't just disappear. It's like that saying, what goes in must come out. KVL states that the sum of all the voltages around any closed loop in a circuit must equal zero. This means that the energy supplied by the source is used up by all the components in the loop. It's like taking a round trip back home. You might go up and down hills along the way, but you always end up back where you started. Now that we know the basic laws governing circuits, let's talk about how we can actually analyze them. There are a few different methods we can use, but we'll focus on two main ones: nodal analysis and mesh analysis. Nodal analysis is like solving a puzzle by focusing on the points where different pieces connect. In a circuit, these connection points are called nodes. By applying KCL at each node, we can create a set of equations that we can solve to find the unknown voltages in the circuit. Mesh analysis, on the other hand, is like solving a maze by systematically exploring each path. A mesh is a loop in a circuit that doesn't contain any other loops inside of it. By applying KVL around each mesh, we can create another set of equations to solve for the unknown currents. Both nodal and mesh analysis are powerful tools for cracking the code of complex circuits. It's like having different tools in your detective kit to solve different types of mysteries, and the best part is, you don't need to be Sherlock Holmes to use them. Chapter 4. Circuit Theorems. Shortcuts for circuit superstars. Okay, sometimes analyzing circuits can feel like you're navigating a maze blindfolded. But don't worry, there are some handy shortcuts we can use to make our lives a whole lot easier. We call these shortcuts circuit theorems. One of the most useful theorems is called Thevenin's theorem. It's like having a magic wand that can simplify any complex circuit into a single voltage source and a single resistor. This makes analyzing the circuit a walk in the park. Another time-saving theorem is Norton's theorem. It's like Thevenin's twin, but instead of a voltage source, it uses a current source and a resistor in parallel. Both theorems are super handy for simplifying circuits and making our calculations a breeze. We also have the superposition theorem, which is like having the ability to break down a complex problem into smaller, more manageable parts. This theorem lets us analyze the effects of each source in a circuit independently and then add up the results. These theorems are like secret weapons in our circuit analysis arsenal. They save us time, reduce errors, and make us feel like electrical engineering rock stars. Chapter 5. Operational Amplifiers, the Swiss Army Knives of Electronics. Get ready to meet the rock stars of the electronics world. Operational amplifiers, or op-amps for short. These little guys are like the Swiss Army knives of circuits, capable of performing a wide range of functions. Op-amps are basically voltage amplifiers with extremely high gain. Think of them like those megaphones that can amplify your voice to ear-splitting levels. But unlike a megaphone, op-amps can do much more than just amplify signals. With a few simple components, we can configure op-amps to perform mathematical operations like addition, subtraction, integration, and differentiation. They can also be used as filters, oscillators, and even voltage regulators. Op-amps are used in countless electronic devices from smartphones and computers to audio equipment and medical instruments. They're like the behind-the-scenes heroes that make our modern world possible. Alright, let's talk about two more important components that add a little spice to the world of circuits, capacitors, and inductors. These guys are like the energy storage units of the electrical world. Capacitors are like tiny rechargeable batteries that store energy in an electric field. They're made of two conductive plates separated by an insulating material called a dielectric. When a voltage is applied across a capacitor, it charges up like a water balloon storing electrical energy. Inductors, on the other hand, store energy in a magnetic field. They're basically coils of wire that resist changes in current. When current flows through an inductor, it creates a magnetic field around the coil, storing energy like a compressed spring. Capacitors and inductors are essential components in many electronic circuits, especially those that involve timing, filtering, and energy storage. They're like the silent partners in a business working behind the scenes to keep everything running smoothly. Things are about to get a little more dynamic as we explore the world of first-order circuits. These circuits contain energy storage elements like capacitors and inductors, which means their behavior changes over time. Imagine charging up a capacitor or energizing an inductor. The voltage and current don't instantly reach their final values. Instead, they change gradually over time, like a roller coaster slowly climbing a hill. We can analyze the behavior of first-order circuits using differential equations. But don't worry, we won't get bogged down in the math too much. The important thing to remember is that these circuits have a time constant that determines how quickly they respond to changes. First-order circuits are used in a wide range of applications, from timing circuits and filters to oscillators and signal processing circuits. They're like the timekeepers of the electronics world, ensuring everything happens in sync. And for our final act, we're taking it up a notch with second-order circuits. These circuits contain two energy storage elements, which means their behavior is even more dynamic and exciting than first-order circuits. Think of a pendulum swinging back and forth or a mass bouncing on a spring. These are examples of second-order systems, and their behavior can be described using second-order differential equations. Second-order circuits can exhibit a wide range of behaviors, including oscillations, damping, and resonance. They're like the acrobats of the electronics world, capable of performing complex maneuvers and stunts. Understanding second-order circuits is crucial for designing and analyzing many electronic systems, from audio filters and oscillators to control systems and power electronics. They're the grand finale of our journey into the world of basic electrical circuits. And there you have it, a crash course on the fundamentals of DC circuits. I hope you enjoyed this electrifying journey into the world of electronics. Remember, understanding the basics is key to unlocking the secrets of more complex circuits and systems. But our journey doesn't end here. In part 2, we'll dive even deeper into the fascinating world of AC circuits, where things get a little more wavy. We'll explore concepts like impedance, reactance, and power factor. Get ready for another thrilling ride through the world of electronics. In the meantime, don't forget to like, subscribe, and smash that bell icon so you don't miss out on the next electrifying installment. And if you have any questions or want to share your own circuit building adventures, drop a comment below. Stay curious, my friends.